Hello, good afternoon. Um, okay, let me know if the music is too loud. If it is too loud, I'll just lower it a bit. If not, then we'll carry on. Okay, right. So how's the volume of the music? Is it too loud? Is it fine? Anyway, we're gonna continue with binomial expansion. So today we're gonna do the last part of the chapter, and then we're gonna combine that with partial fractions, and then we'll do a couple of example questions, and then you should be off to the races, so to speak. You can start doing the past years after that. Okay, so the general binomial expansion. So just to briefly remind you what the binomial expansion for positive integers look like, say you have a plus b to the power of n, and in this case your n is a positive integer. Then when you expand this, you would get n0, a1, bn. Oh, sorry, this is a0. And then n1, a1, bn minus 1. And this goes on all the way to nn, an, b0. Okay, in summation notation, you would write this as the sum from r equals to 0 to n of a r bn minus r. But this is only for positive integers. So today we're gonna do the one for any real number. It doesn't have to be positive. It can be negative. It can even be a fraction. It can even be an irrational number like pi, whatever. Anything works. So the way this one works is you have to do it like this. A plus b to the power of, let's say, n. And the way you expand this is, how should I explain this? The notation is something that you haven't actually seen before because it involves a product. I'll just write it out. Maybe that might make the most sense. So this actually looks like 1 over 0 factorial a to the power of 0 b to the power of n. Okay, so far it's kind of similar. And then plus, this one is going to be 1 times n over 1 factorial a1 bn minus 1. And then the third one is going to be 1 times n minus 1 over 2 factorial a2 bn minus 2, and so on. Not sure whether you are seeing the pattern here, but let me try to do a few more and then you can hopefully see where I'm getting at. So it goes there. That goes right there. Okay, so if we continue with this, I'm going to get 1 times n minus 1 times n minus 2. You see these guys here, they always become 1 less, and then you multiply it. So this is actually like a product of r equals 0 to n. Well, technically it's r equals 0 to infinity, and then this is actually you know what, maybe I should introduce this because this is not something in your syllabus. It gets a bit too complicated. Just ignore that. Times over 3 factorial times a cubed bn minus 3 and so on. And unlike the regular binomial expansion, this is actually an infinite series. It goes on forever. Okay, so let me do an example here. Quick example. Let's say we have 2 plus x to the power of 1 over 2. So the way you expand this is you first write 1 over 0 factorial 2 to the power of 0 x to the power of 1 over 2 plus 1 times 1 over 2 over 1 factorial 2 to the power of 1 x to the power of half minus 1, so that's 1 negative 1 over 2 plus 1 times a half. Half minus 1 is negative a half divided by 2 factorial, and then 2 to the power of 2 x to the power of negative 3 over 2. And you can see this keeps going forever because you can never get to a point where it terminates, unlike the binomial expansion. So this one is going to be negative 3 over 2 and then 3 factorial 2 to the power 3 x to the power negative 5 over 2, and just goes on forever. So usually in the exam, they would ask you to find the first 3 terms or the first 2 terms. They won't ask you to list all the terms because there are an infinite amount of terms. Okay? Alright. Hang on, let me make my pointer bigger. So, since I claim that this is the general formula for the binomial expansion, what if I replace n with what if I replace this n here with an integer? Would this general formula reduce to this one? The answer is yes. For example, let's say I put one plus x to the power of 3. Okay, and I'm going to expand this using the general binomial expansion. So using the regular binomial expansion, we kind of know what we're going to get, right? But using the general one, are we going to get the same thing? We should, because maths, well, it should be consistent. Technically, the answer is maths is not consistent, but that's a topic for another day. But in most cases, maths is consistent. So, let's try to expand this using this guy here. What do we get? We have 1 over 0 factorial, 1 to the power of, oh sorry, this power 0, x to the power of 3. Cool. Next one we have 1 times 3 over 1 factorial times 1 to the power of 1x squared plus 1 times 3 times 2 over 2 factorial, and then this one would be 1 to the power of 2x1 plus 1 times 3 times 2 times 1 over 3 factorial. This is 1 cubed x. This is going to be 3 minus 3, which is 0. And then it terminates, it stops here. Okay, and the reason it terminates, I mean, you could argue and say, what do you mean? Shouldn't it continue on? Well, yes, it continues. So let's try doing the 5th term, and then you'll see where it terminates. So if I were to do the 5th term, I'm going to get 1 times 3 times 2 times 1 times 0 over 4 factorial. 1 to the power of 4, x to the power of negative 1. You see I'm multiplying by 0 here, which means this entire term is actually 0. If I continue on to the 6th term or any subsequent terms, I will always have a 0 in there. So this is also 0, which means all the subsequent terms after the 4th term just vanishes into thin air. Oh, it's a bit too loud, is it? Okay, let me drop that a bit. There we go. Hopefully that's better. Is that better? It's a bit distracting, sorry. Sorry about that. Because I can't actually hear the music on my end. I just sort of... Because if I turn on the music here, then it's gonna go into the mic, and then you're gonna get some feedback loop. So the music's only on your end, not on my end. So if it's too loud or if it's too distracting, let me know. I will either turn it off or lower the volume. Okay, so as you can see, these terms after the 4th term, they vanish, right? So we can actually stop here. And the reason it stops is because eventually you get 0. But if you look at these terms here, if this is a non-integer value, you would actually sort of skip the 0. So there will never be a point where you're multiplying by 0, which means this series goes on forever. Okay? Right. So if you try to expand this, you'll see that you get x cubed plus 3x squared plus 3x plus 1, which is exactly what you would expect from the regular binomial expansion. So this is the more general form, so to speak. The one that you've learned in AdMath and in AS Math, this is the more special case kind of thing. Okay, so at this point you might be wondering, how do you prove the general form of the binomial expansion or the binomial expansion in the first place? Well, in order to prove this, you need something called the Maclaurin series, which is a special case of the Taylor expansion. However, those of you who are not doing further maths, you will not be covering the Maclaurin series. Those of you who are doing further math, once you get to differentiation, I believe that's the next chapter. Towards the end, they've actually introduced a new topic called the Maclaurin series. So using that, you can actually prove the binomial expansion. I'll just briefly show you what it looks like. Something like this. Expand that. There. So if you differentiate something repeatedly, you will get a pattern. And then if you use the Maclaurin series expansion, you put the pattern in, and then you expand this shenanigans, eventually you get the binomial expansion. If you want to do that for the non-integer value thing, the expansion never ends, and instead you get a product. And eventually you get the general binomial expansion formula, and you can use that for some examples down here. Yeah. But anyway, this is not in your syllabus, so you don't have to worry about this. But in case you're curious, that's where it comes from. Okay, anyway, we are done with this. So now we are going to do more examples. But let me show you another example. Let's say you have one over... Oh wait, actually, there's something important I need to mention. So if you look at your data booklet for your formats, you'll see that they don't actually give you something like this. Oh, thanks for the follow, Sprout. Hello. But instead, what they would give you in the data booklet kind of looks like this: 1 plus x to the power of n. So they've actually simplified it so that the first term in the binomial expansion is the 1. And it is highly recommended that you do that as well, because it makes the calculation a lot easier. So you see that in the book, it gives you something like 1. Okay, you know what? Let me just expand this, then you see what I mean. If I expand this, I'm going to get 1 over 0 factorial. And then we get 1 to the power of 0, x to the power of n, and then plus 1 times n over 1 factorial, 1 to the power of 1, x, n minus 1, n minus 1 over 2 factorial 1 squared is n minus 2 plus 1 n minus 2 over 3 factorial 1 cubed x n minus 3 plus dot dot dot. And if you simplify this, you see that this just becomes... Wait a minute. Oh, I think I did it the other way around. So in the book, I think they've swapped this around. So this is n, this is 0. They swapped the order around, but it actually doesn't matter because it is symmetrical anyways. Hey, thanks for the follow, Jolami. So this is going to be n minus 1, 1, n minus 2, 2, n minus 3, 3, and so on. So you can see here that 1 to the power of any number will just give you 1, but this one will give you 1 over here because x to the power 0 is 1. This one will actually give you n times x. Next one is n times n minus 1 over 2 factorial, and then x squared, and next one is n minus 1, n minus 2, 3 factorial x cubed, and so on. So this is the formula that's given to you in the data booklet. Okay, this guy right here. However, there are certain conditions associated with using this formula. So the first condition is that the magnitude of x must be less than 1. And then n is any real number. Okay, so this guy must be less than 1. So the reason for this has to do with the convergence of the series, if I'm not mistaken. I think there's an alternate way of deriving this guy using the geometric series, but I'm not sure, and I think that's where it comes from. However, like I said, I'm not sure. If I've worked out why exactly this is the case, I will let you guys know. But for now, just know that the condition is going to be less than 1. Okay, so we'll do some passive questions and then you see how to apply this condition. They will sometimes ask you to check this, or they'll ask you for the domain of x, which means you have to do this. Okay, so let's do some more examples. Let's say we have 3 over 1 plus x squared. Okay, and then they say find the first 3 terms of the expansion. So what you want to do is you take the 3 out, and then essentially you're left with 1 plus x to the power of minus 2. Okay, and then now you can expand this using the general binomial expansion. So when you expand this, you're going to get 1 plus negative 2 times x plus negative 2, negative 3 over 2 factorial times x squared plus negative 2, negative 3, negative 4 over 3 factorial x cubed, and so on. So normally the question would say find the first 4 terms or the first 3 terms, so you know where to stop. And then you expand the 3 in, you will get 3 minus 6x. This guy is going to be 6 divided by 2, which is 3, so you get plus 9x squared. And then you have 6, 4, 24, divided by 6 is 4, 4 times 3 is 12, so minus 12x cubed, and then dot dot dot. Remember to put the dot dot dot. Okay, there you go. Now, what if they give you an expression where the first term is not a 1? Let's say something like 3 minus 2x to the power of 1 over 3. Okay, the first thing you do is you want to make sure the first term here is a 1. Right, so how do you do that? Well, you could imagine factorizing out a 3. So this becomes 1 minus 2 over 3x. And then you use the rules of indices to multiply the power in. So you have 3 to the power of 1 over 3, 1 minus 2 over 3x to the power of 1 over 3. So this is actually the cube root of 3, which you can leave there. And now you can expand this guy here using the general binomial expansion, because the first term is a 1. Okay. You should also check and make sure that the magnitude here is less than 1. As you can see, if I take the magnitude of negative 2 over 3 x, well, you don't have to put the x actually. How should I explain this? Okay, you know what, I'll just do it like that. You see, this is actually 2 over 3, which is less than 1. So this is fine. Anyway, so let's expand this. We are going to get 1 plus 1 over 3 times negative 2 over 3 x plus 1 over 3 times negative 2 over 3 over 2 factorial times negative 2 over 3x squared plus 1 over 3 negative 2 over 3 negative 5 over 3 over 3 factorial negative 2 over 3x cubed, and then dot dot dot, and then you expand this and you get your answer. Okay, now what if we have another example? Let's say it looks like this: x minus 2 to the power of half. So x minus 2 is the same as negative 2 plus x. Okay, so now you want to make sure that this guy is a 1. So what you can do is you can factorize a negative 2 out. So this becomes negative x over 2. This whole thing to the power of 1 over 2. And then you square root negative 2. Obviously, you can't square root a negative number. Let me just go back in time and get rid of the negative. You did not see that. Oh, okay. Then next you're going to put this down here, and then you expand normally, right? So this you can see here, this is what this form looks like, and you just expand that normally. Oh, sorry, this should be a plus. And then expand, and you get your answer. Done. Okay, there you go. Right, let's do some examples. Okay, let's do this one. Oh, oops. Let's move this guy here, and then I'll paste it here. Okay, so if you look at this, the first part of this question, they want you to express it in partial fractions, which is something that you already know how to do. So we'll start by comparing the numerator. I'm gonna skip a few steps and jump right to the third step, because by now you should know what I'm trying to do here. So this is actually 5x squared minus 7x plus 4, okay? I should mention that you should always check and make sure that the degree of the numerator is smaller than the degree of the denominator, which it is in this case, so it's fine. Okay, next thing is we're going to put in some hypothetical values of x. Let's say we put x is -2/3. So b would disappear, and then we would get 4/9 plus 5, which is 49/9. A is actually 2. Okay, so now that we know what A is, we can substitute some random value for x. So let's say x is 0, which means we have 2 times 5 is 10, plus 2b equals to 4, which means b must be -3. Therefore, our function is going to be 2/3x plus 2 plus, well, I should put a minus actually, minus 3/x² plus 5. Oh, hang on a second, this is a quadratic. Oops, which means I should actually put this as bx plus c. My bad, I actually forgot about that. I completely messed up here. Oopsie daisy. Sorry. Let me just rewrite this actually. So this should actually be bx plus c times 3x plus 2. Yep. Okay, let's do that again. Let's say x is 0, which means we would have... No, let's go with x is -2/3. So we'll still end up with the same thing. A is still going to be 2. And then when x is equals to 0, b would disappear, which means we have 10 plus 2c equals to 4. So c is going to be -3 again, but now we have to find b. So let's say we put x is 1. So we would have 2 times 6 is 12 plus b minus 3. And then we have 3 plus 2 is 5. Minus 2 plus 4 is 2. So we get 12 plus 5b minus 15 equals to 2. So minus 3 plus 3, 5. B is 1. There we go. Therefore, our function of x, when you expand it in partial fractions, is going to be 1/3x plus 2 plus x minus 3 over x squared plus 5. There. Okay. Next, let's do part 2. Obtain the expression in ascending powers of x up to and including the term x squared. So, how do we do this? They want you to expand. And you can see there are 2 terms over here. So you have to expand the 2 terms, and then you have to combine them, and you have to include up to x squared. Get rid of the other terms. So let's try to expand 1 over 3x plus 2 first. You can see that the first term is not a 1. Let's try to factorize something so it becomes a 1. Oh, by the way, let me just go back here. I just realized something. This thing that I mentioned earlier, where was it? Yep, ignore this one. Just realized you have to actually include the x in there for it to actually make sense. For example, say this guy here. To find the domain in which this expansion would make sense, what you are supposed to do is you're supposed to go negative 2 over 3x, and then you put less than 1. And then this actually becomes, if you square, well, if you remove the modulus, well, by squaring both sides. Wait, actually, this is a modulus function with an inequality. You're supposed to sketch the graph. So for this one, you actually have y equals to negative 2 over 3x and y equals to 1. So negative 2 over 3x kind of looks like this, and y equals to 1 kind of looks like this. So you're trying to find a point where this graph is less than this graph, which means you want to take all the points that are greater than this critical point. So to find the critical point, you start by equating these two guys. So x must be 3 over 2, which means this point is x equals to 3 over 2. Therefore, your answer is x is greater than 3 over 2. And that's the domain for the expansion to be valid. Okay, you have to use what we've learned in the first chapter to work this out. Okay, come back here. We'll do an example related to that later. Okay, so let's try to expand this guy here. We get 2 minus 1. This is 1 plus 3 over 2x. The power of minus 1, and then this one is 1 over 2. This one we expand normally, we have 1 plus minus 1, 3 over 2x, plus minus 1 minus 2 over 2 factorial, 3 over 2x squared. And then we can stop there because we are only interested in up to x squared. We don't care about x cubed and so on, so we just ignore the rest. Alright, let's expand this and see what we get. We get a half minus 3 over 4x plus 9 over 8 x squared. Okay, then we can stop here. So next we're going to try to expand this guy here. Okay, so let's do that down here, I suppose. So we have x minus 3 times x squared plus 5 to the power of minus 1, which is going to give us I'm not quite sure what you mean. If x is 0, that means you're replacing all the x's here with 0. So this one will give you 5 times a, 5 times a is 2, so you get 10. And then when x is 0 here, b disappears. When x is 0 here, you get 2. So 2 times c is 2c. When x is 0 here, you get, this is 0, which means you get 4. So 4 minus 10 is negative 6. Negative 6 divided by 2 is negative 3. No, I think it's correct. Did I miss something? Okay. Okay, so let's expand this guy. Let's make sure it looks like this first. Okay, so here we have x minus 3 over 5 times 1 plus x squared over 5 to the power of minus 1. Now we're going to try to expand this guy and see what we get. We have 1 plus negative 1 x squared over 5 to the power of, well, 1. And then we have the next one, but the next one is going to give us x to the power of 4. So we don't care about that, which means we just ignore it. So now we have to expand these in. So which expansion will give us x squared? So you see, if I take x times x squared, I will get x cubed, which means we don't need to do that expansion. But if we take negative 3 and times it with this, we will get x squared. So we need to do that. So everything else aside from x times this one. So we're going to take x over 5 times 1. Okay, because this guy here is actually x over 5 minus 3 over 5. So I'm sort of imagining it split up into 2 terms, and I'm expanding them individually. So I'm going to take x over 5 times 1. That gives me x over 5. And then we'll take negative 3 over 5 times 1. Negative 3 over 5 times the x squared term. Last dot dot dot. Okay, so now that we've expanded both this term and this term, we get this and this. Now when we combine them together, we are going to get our answer. So let's do that right here. Combine this guy with this guy. So 1 over 2 minus 3 over 5. What do we get? Get negative 1 over 10. 3 over 4, negative 3 over 4, plus 1 over 5. We get negative 11 over 20x. Next we have 9 over 8 plus 3 over 25, which gives us 249 over 200x squared plus dot dot dot, and then we can stop there. Okay, let me just make sure I got the expansion right and just check the answer. 2, 1 minus 3, okay. Nani? Seems like I might have messed up the expansion a bit. I should get 2 over 5 for the first one, then negative 13 over 10. Uh-oh. Why did I mess up? Oh! I think I forgot to divide by Wait a minute. Oh, this should be divided by 2 factorial. This should be divided by 3 factorial. Oops, my bad. Let's get rid of this. Okay, so this one should actually be divided by 2 factorial. This is divided by... Wait, is that right? This is 0 factorial, and then 1, then this is 2. Oh no, it is correct. No, it is correct. Okay. 1 factorial, this one is 2 factorial. Okay. Did I make an algebraic error then? This should be a half plus something. This one should be -3 times 1, so it's -3 over 5. So if you add them together, you should have 1 over 2 minus 3 over 5, which is -1 over 10. The answer is 2 over 5. What? Wait, let me check my partial fraction again. We have A is 2, 2, 1 minus 3. Wait. Oh, this is 2. Why did I put a 1 there? Oh, you guys didn't mention anything. This should be a 2. No! Alright, which means this is not there anymore. This should actually be a 2 over here. Which means you would end up with 1. So 1 minus 3 over 5 is 2 over 5, which is a 1 over 10, which is what? No. 2 over 5. Is that the answer? Let me just check. 2 over 5. Yep, okay. Okay, I think that was the problem. Yeah. So this would actually give us 1 right here. So this is actually -3 over 2x. This is going to be plus 9 over 4x squared. Okay, and this guy here, we will expand this, we will get plus x over 5 plus 3 over 25x squared. Now when we combine them together, we will get 2 over 5 here. And the next one is -3 over 2 plus 1 over 5, which is -13 over 10x. And the last one is 9 over 4 plus 3 over 25, which is 237 over 100x squared. And I believe that should be the answer. Yep, there we go. Okay, so there it is. Okay, let's do one more question. This question, I'm gonna try to find one where you have to use the modulus of x is less than 1 thingy. Aha. This one. The very first question. Okay, expand 1 plus 3x to the power of -1/3 in ascending powers up to x squared. Okay, so that's going to give me 1 plus -1/3, 3x plus -1/3, and then we take -1/3 minus 1, which gives us -4/3, and then multiply that with 3x squared, and we're done. There we go. Part B. State the set of values of x for which the expansion is valid. So how do you check? You start by doing the modulus of 3x is less than 1. So basically you just take the modulus of the second term and you set that to be less than 1. So if you think about this in terms of the graph, 3x is actually a line that goes through the origin, and y equals to 1 is a horizontal line like so, and you're trying to find the line, the part of the line where the 3x graph is less than the 1 graph. So that means you want these points. So you need to find what this intersection point is. So you just equate 3x equals to 1, x equals to 1/3. So that will tell you what the intersection point is, which is 1/3. Therefore, you're only interested in the values of x where it is... Oh, wait a minute, I forgot. This is actually, you need to put modulus of x, which means you're actually reflecting this up here, like so. I forgot to put the modulus there. My bad. Which means you're only interested in the points between these two extremes. Okay, so what is the other point here? Well, this other point has to be x equals to -1/3. Which means your final value should be, the final range should be between -1/3 and 1/3. And that's how you check which values of x is the expansion valid for. So whenever you see this term here, blah blah blah, expansion is valid, this is what you want to do. Okay, and that's it. We are done with this chapter. Finished. Okay, so you should be able to do all the passive questions on your own now. If there's anything that you're stuck on, just let me know. Okay, and I'll let you carry on with the rest of the past years on your own. Okay, we'll stop here for today. And next class, we're going to continue with a new chapter. So I would highly recommend that you give this a go. If there's anything that you want me to discuss next class, please let me know. Otherwise, I will assume that everyone is okay and we're gonna move on to the next chapter. Alright, I'll see you guys then. Bye bye. Those of you taking physics, I'll see you at 3. Bye. Oh, hey Bella, hello. Bye bye.